Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year is 1917. Europe is embroiled in a devastating war, yet amidst the chaos, a remarkable intellectual project takes shape. Zygmunt Janiszewski, a Polish mathematician, pens a document of extraordinary foresight on the needs of mathematics in Poland. This was a mere academic treatise. It was a bold, audacious blueprint for a national mathematical school within a nation that, at that moment, existed only as a nascent hope, a dream yet to be realized on the world stage. Poland, partitioned for over a century among Russia, Prussia, and Austria-Hungary, lacked a unified scientific identity. Its intellectual life remained decentralized, fragmented, a constellation of isolated stars rather than a cohesive galaxy. Brilliant Polish minds, lacking a robust national academic infrastructure, often sought opportunities elsewhere, their talents enriching other nations' scientific landscapes. Janiszewski recognized this profound intellectual diaspora. He saw a critical need to consolidate and cultivate Poland's mathematical potential to forge a distinct, internationally recognized mathematical identity for the scattered fragments of its past. His approach, however, was far from conventional. He did not propose a broad, sprawling program mimicking the established mathematical powerhouses of Europe. Instead, he envisioned a strategy of focused excellence, a concentrated investment in a specific area of mathematics poised for rapid advancement and global impact. His vision centered on a radical concentration of set theory, topology, and the foundations of mathematics. These were nascent fields, ripe for groundbreaking discoveries. By focusing national resources on these areas, Janiszewski believed Poland could leap from established mathematical centers, achieving global leadership in a relatively short time. This was a daring gamble, a calculated risk predicated on a belief that a small, highly specialized group of researchers could achieve more than a larger, more diffuse one. This strategic insight, concentrating limited resources for maximum impact, would later become a cornerstone of effective academic and scientific planning, transcending the specific context of early 20th century Poland. Central to Janiszewski's plan was the creation of a specialized journal, Fundamenta Mathematicae. This journal, to be published in prominent European languages, would serve as a crucial instrument in bypassing linguistic barriers and ensuring immediate global dissemination of Polish mathematical achievements. It was a recognition that scientific progress thrives on open communication and international collaboration. The journal wouldn't simply publish Polish work, it would become a vital platform for international discourse in topology and related fields, attracting contributions from leading mathematicians worldwide, thus solidifying Poland's position at the forefront of mathematical research. Janiszewski's proposal was more than a mere academic plan. It was a testament to his profound understanding of the dynamics of scientific progress and national development. He recognized that scientific achievement is not simply a matter of individual brilliance, but also a function of strategic planning, resource allocation, and effective communication. His vision transcended the limitations of his time, providing a powerful model for nations and institutions seeking to establish themselves as leaders in specific scientific domains. The strategy he proposed, a concentrated effort on a niche area of research, coupled with a commitment to international collaboration, echoes through modern approaches to academic and industrial research. The concentration of resources on a specific area rather than a broad dispersion proved to be a remarkably effective approach, demonstrating that quality often surpasses quantity in scientific advancement. His proposal was a symphony of strategic thinking, recognizing the potential of a small, highly focused group to achieve extraordinary results. It was a bold vision, a testament to his confidence in the potential of Polish mathematicians, and a recognition of the importance of strategic planning in achieving national scientific prominence. The plan was not merely to catch up with established centers, it was to surpass them by focusing on areas where Poland could rapidly gain a competitive edge. This audacious plan, conceived amidst the turmoil of war, would lay the foundation for a remarkable chapter in the history of mathematics, a chapter that would solidify Poland's position on the world stage, not through sheer size, but through focused excellence and strategic brilliance. The impact of this single document, this blueprint for a mathematical future, would further outstrip the confines of its initial context, becoming a lasting testament to the power of visionary leadership and strategic thinking in the advancement of science. This was the genesis of a remarkable story, a story that would soon transform a fragmented scientific landscape into a vibrant center of mathematical innovation. The grand strategic architecture for Polish mathematics, conceived in the crucible of war, required an equally powerful intellectual engine. A vision for a world-leading research center is one thing. The actual mathematical substance capable of fueling it is quite another. For Zygmunt Janiszewski, the blueprint for the institution and the blueprint for a new understanding of space were two sides of the same coin. The profound originality of his plan rested upon the profound originality of his own mathematical research. This work unfolded within the nascent, exhilarating, and often bewildering field of topology, a domain where mathematicians were challenging the deepest intuitions about shape, continuity, and dimension. At the dawn of the 20th century, the discipline known as analysis was undergoing a radical transformation. The familiar, well-behaved curves and surfaces of Euclidean geometry were giving way to a menagerie of bizarre and counterintuitive objects. Georg Cantor's set theory had provided a new language, and with it, mathematicians began to construct forms that defied easy visualization. There were space-filling curves, indecomposable continua that behaved like tangled, indivisible masses, and sets so porous they seemed to exist between 1 and 2 dimensions. These were the so-called pathological monsters of topology, and they posed a fundamental challenge. The old geometric vocabulary was inadequate. The field needed a new set of rigorous tools, a way to classify these strange entities and understand their fundamental properties, particularly the most basic property of all, how a set carves up the space around it. The central question became one of separation. When does a collection of points in the plane act as a fence, and when does it remain a permeable feature? Into this intellectual phrase stepped Janiszewski, whose 1911 doctoral dissertation, submitted to the Sorbonne under the supervision of Henry Lebesgue, announced the arrival of a formidable new talent. His approach was characterized by a rare synthesis of abilities. He possessed a powerful, almost physical intuition for the behavior of complex geometric forms, an ability to see in his mind's eye how twisting, connected sets would interact within the plane. He coupled this geometric sensibility with an unyielding commitment to the precision of set theoretic language. His work sought to translate visual insight into logical certainty. He focused his formidable intellect on the topology of the Euclidean plane, the two-dimensional space represented as r squared. He pursued a deep understanding of how subsets of this plane relate to one another, how they connect, and how they divide. This intense investigation culminated in the result for which he is most celebrated, a theorem of breathtaking elegance and utility that now bears his name. Janiszewski's theorem addresses the problem of separation with profound simplicity. Consider two continua in the plane, that is, two sets of points that are both closed and connected. Think of them as two distinct landmasses on a map. The question is, does their union, the combined territory of both landmasses, enclose a region? Does it create an inland sea from which there is no escape? Intuition might suggest a complicated answer depending on their shapes, sizes, and relative positions. Janiszewski's theorem bypasses all such geometric complexities. It states that at the intersection of these two continua is itself a connected set. If our two landmasses are joined by a single, unbroken isthmus, then their union fails to separate the plane. The plane remains a single, unified territory. The power of this statement is immense. It transforms a global question about the entire plane into a local one about the nature of the intersection. One need only examine the character of the points shared by the two sets. If that shared region is connected, the larger question is answered. This principle and its corollary, which provides conditions for when a set asterisk does asterisk separate the plane, became a cornerstone of plane topology. It armed mathematicians with a reliable and simple tool for dissecting the structure of the plane, allowing them to prove results that were previously accessible only through long, tortuous arguments. It is a perfect example of a purely topological insight. The properties of shape and scale are stripped away, leaving only the fundamental architecture of connection. This inquiry into the structure of the plane naturally extended to a deeper examination of the building blocks themselves, the continua. Janiszewski made crucial contributions to the understanding of what were called irreducible continua. An irreducible continuum between 2 points, say point A and point B, is a connected set containing them both, with a remarkable property that no smaller, proper subcontinuum within it also connects A and B. It is, in a topological sense, the most efficient possible connection. Removing almost any single point from its interior severs the link. These are often highly complex, serpentine objects, and Janiszewski developed key theorems that characterized their structure, revealing, for instance, that many such continua are composed of layers, like an onion, of other indecomposable continua. His work further illuminated the crucial concept of local connectedness. A space is locally connected if, for any point within it, one can find arbitrarily small connected neighborhoods around that point. This property formalizes the intuitive idea of a space being pack-connected at a microscopic level. It excludes the strange behavior seen in objects like the topologist's sine curve, which approaches a limit line but remains fundamentally disconnected from it. Janiszewski, working alongside his future colleagues Warsaw Sierpinski and Stefan Mazakiewicz, helped to forge the monumental link between this property and the classical notion of a curve. Their collective work established that a continuum is locally connected if and only if it is a continuous image of a line segment. This result was a triumph. It provided a rigorous, topological answer to the ancient question, what is a curve? It tamed the pathological monsters by providing a clear criterion for well-behavedness, showing that the spaces with this property were precisely the ones that could be drawn without lifting the pen. The body of this mathematical work formed the intellectual bedrock for Janiszewski's grand organizational vision. His theorems were the foundational capital, the proof of concept that a new, focused approach to mathematics to yield spectacular results. His style of research, combining geometric intuition with set theoretic rigor, was the very methodology he envisioned for an entire school. The plan for a Polish journal and a center for foundational study was credible because Janiszewski himself was already producing the exact kind of brilliant, foundational mathematics he hoped to foster. This deep well of personal scientific achievement was the essential prerequisite for the next, even more audacious phase of his project, the translation of these abstract, mathematical ideas into a living, breathing, world-changing institution. The armistice of 1918 and the subsequent rebirth of the Polish state provided the dramatic, atheotic stage upon which this translation from abstract idea to tangible institution was to occur. The intellectual capital accumulated through Janiszewski's theorems on continua now faced its ultimate test, deployment in the real world, a world of competing urgencies, where the very survival of a newly independent nation depended on establishing borders, building an economy from the ashes of partition and war, and forging a coherent national identity. Within this crucible of state building, the argument for establishing a world-class center for pure, abstract mathematics might have seemed a luxury, a distant dream for a more stable future. For Janiszewski and his circle, however, it was an absolute necessity, a strategic imperative for positioning Poland on the intellectual map of the 20th century. The project required more than a brilliant mind. It demanded a triumvirate of complementary talents. Janiszewski, the visionary architect, found his indispensable partners in Warsaw Sierpinski and Stefan Mazakiewicz. Sierpinski, already a mathematician of international stature, possessed the breviers and established reputation to lend the enterprise immediate credibility. Mazakiewicz, a fellow topologist of extraordinary power, and Janiszewski's friendly rival in solving deep problems, provided another pillar of pure intellectual strength. Together, they formed a leadership corps with a shared conviction that Polish mathematics could achieve global prominence through intense specialization. They moved with a speed and unity of purpose that belie the surrounding political and social turmoil. Their first maneuver was to secure the intellectual high ground within the nation's premier academic institution, the University of Warsaw, repolonized in 1915 and now the flagship university of a sovereign state. became their base of operations. Through their collective prestige and the undeniable force of their shared vision, all three secured professorships, effectively creating a department within a department. This concentration of force was the initial critical step. It established an institutional anchor, a place from which to attract students, secure resources, and launch the most audacious component of their plan. This component was the creation of a journal and organ that would serve as the voice, the engine, and the global advertisement for their new school of thought. The result was Fundamenta Mathematicae, a publication whose design was as revolutionary as the mathematics it would contain. Its first volume appeared in 1920, an act of profound intellectual optimism in a country still fighting for its borders. The journal's very existence was a statement. Its strategic brilliance, however, lay in two key principles articulated in Janiszewski's original blueprint. The first was its radical specialization. Before Fundamenta Mathematicae, mathematical journals were typically generalist affairs. A paper on number theory might appear alongside one on celestial mechanics or differential geometry. This new journal, by contrast, declared its focus with its title The Foundations of Mathematics. It would publish work exclusively in set theory, topology, logic, and the theory of real functions, the very fields where the Polish school intended to dominate. This created an unprecedented density of related ideas. For researchers in these fields, it became the essential periodical, a one-stop repository for the most advanced work, accelerating the pace of discovery by placing every new result in immediate conversation with all others. The second principle was its linguistic policy. Rather than publishing in Polish, which would have confined its readership and impact, the journal accepted papers in the major international languages of science: French, German, and English. This was a masterstroke of strategic internationalism. It ensured that the work of Warsaw's mathematicians would land directly on the desks of their colleagues in Paris, Göttingen, Berlin, and Princeton without the friction of translation. It was an open invitation to the world's leading figures to engage with and publish in the journal. It signaled that the Warsaw School saw itself as a global and a leading player from its very inception. The journal was a magnet for talent and a conduit for influence, drawing the world's attention to Poland while simultaneously projecting Polish thought onto the world stage. The effect was immediate and profound. The first volume itself was a landmark, containing foundational papers by Sierpiński, Mazurkiewicz, Kwiatkowski, and other emerging Polish luminaries, alongside contributions from established international figures. It was a physical embodiment of Janiszewski's vision, a proof that a small group of determined individuals in a nascent state could create an institution that commanded global respect. The journal became a powerful engine of recruitment. A promising young mathematician anywhere in Poland knew that the path to a significant career in foundational studies led directly to Warsaw. There, they would find the world's leading experts, a cohort of brilliant peers, and, crucially, a direct and rapid pipeline to publication in the world's most important journal in their field. This system, this intellectual machine designed by Janiszewski, began to produce results at an astonishing rate. The concentration of talent created a vibrant, competitive, and collaborative atmosphere. Problems were posed in seminars on Monday, furiously attacked throughout the week, and sometimes solved by Friday. The rapid publication cycle of Fundamenta Mathematicae meant that these breakthroughs were disseminated to the international community with unparalleled speed. This virtuous cycle cemented Warsaw's reputation. The school became synonymous with modern topology and descriptive set theory. It began to produce a second generation of giants, figures like Kazimierz Kwiatkowski, whose later textbook on topology would become the standard for decades, and Alfred Tarski, whose work would revolutionize logic and formal semantics. The creation of the Warsaw School of Mathematics and its flagship journal stands as a singular case study in the history of science. It demonstrates how a meticulously crafted strategic plan, executed with conviction and precision, can build a world-leading intellectual center from a foundation of little more than talent and a powerful idea. The school's success was a testament to the clarity of the original vision, the understanding that in the modern scientific world, prominence could be achieved through focused excellence. By choosing a specific, fertile, and burgeoning field, and then building an entire institutional apparatus to support its exploration, the Polish school could outperform larger, wealthier, and more established centers. The machine was built, its gears were turning with astonishing speed, and the Warsaw School of Mathematics was becoming a global force. The blueprint had proven itself to be a work of genius, poised to reshape a whole domain of human thought. Yet, this intellectual machine, this engine of abstract thought, was forged in the crucible of an intensely physical and political struggle. The vision for Polish School of Mathematics was inseparable from the vision for a sovereign Poland. For Zygmunt Janiszewski, the pursuit of topology and set theory was an act of profound patriotism, a way to build cultural and intellectual capital for a nation that, for over a century, had been a ghost on the map of Europe. His life's work was a declaration that a reborn Poland would contribute to the highest echelons of human civilization. This conviction was something he was willing to defend with his life, and he did so repeatedly. During the First World War, he laid down his mathematical manuscripts to join the Polish legions, the military formation fighting for Polish independence under Joseph Pilsudski. He served with distinction, a topologist in the trenches, his mind capable of navigating the most esoteric continuum while his body endured the brutal realities of modern warfare. He saw combat on the front lines, an experience that gave his later academic urgency a palpable, existential weight. For him, the university was a second front, a place where the intellectual sovereignty of his nation would be secured. The abstract problems he posed in his doctoral thesis and his subsequent articles were pieces of a larger project, the construction of a national identity grounded in world-class intellectual achievement. With the end of the war in 1918 and the miraculous rebirth of the Polish state, Janiszewski's plan moved from a theoretical ideal to a concrete institutional reality. He threw his entire energy into its implementation, securing the professorships, founding the journal, and gathering the talent that would form the school's core. The future he had fought for was arriving. Then, in 1920, as a fledgling republic faced a new existential threat from the East in the Polish-Soviet War, Janiszewski once again answered the call to serve. He volunteered for the army, preparing to defend the very existence of the nation he was so brilliantly helping to build. It was in this period of immense national peril and feverish intellectual creation that fate delivered its final, cruelest blow. While in Elwal, another vibrant center of Polish mathematics. Janiszewski fell victim to the great global scourge of the era, the Spanish flu epidemic. The influenza that had claimed millions across the world found the 31-year-old visionary. In January of 1920, the mind that had conceived of a reusable continuer and a new future for mathematics was extinguished. The timing was an act of profound historical tragedy. The first volume of Fundamenta Mathematicae, the journal that was the centerpiece of his grand strategy, the physical embodiment of his life's ambition, was at that very moment being prepared for publication. He would never hold a copy. He would never see the global acclaim it would receive. The architect of the entire enterprise was gone before the doors to his cathedral could officially open. The legacy of Zygmunt Janiszewski, therefore, is one of the most poignant and powerful in the history of science. It is the legacy of a master planner who drew up an astonishingly detailed and effective blueprint, laid the foundational stone, and then vanished. His influence is measured less by the list of theorems bearing his name, brilliant as they are, and more by the magnificent structure that his colleagues following his designs were able to erect in his absence. Wacław Sierpiński and Stefan Mazakiewicz, the other two pillars of the early Warsaw School, became the builders who saw the project through. They possessed the founder's vision, a document so clear, so prescient, and so perfectly attuned to the intellectual currents of the time that it served as an infallible guide. The Warsaw School of Mathematics flourished exactly as Janiszewski had predicted. Fundamenta Mathematicae became the world's leading journal for set theory, topology, and the foundations of mathematics. Its pages became the definitive chronicle of an entire field's development, publishing landmark papers by Kuratowski, Tarski, Ulam, and von Neumann, among countless others. The focused strategy worked. Warsaw became a global pilgrimage site for topologists and logicians. The intellectual ecosystem Janiszewski designed was self-perpetuating, generating new talent, new problems, and new fields of inquiry for decades. Its influence spread outwards, with its members eventually seeding departments across the world, particularly in the United States after the devastation of the Second World War. In the final analysis, Janiszewski's contribution transcends the specific problems he solved on the blackboard. His true genius lay in institutional design, in the understanding that intellectual progress is a social and strategic endeavor. He recognized that great science requires more than great scientists. It requires a culture, a focus, a means of communication, and a shared sense of purpose. He provided all of these. His life, though tragically abbreviated, offers a profound lesson on the nature of impact. It demonstrates that the most enduring creations are sometimes the ideas themselves. A theorem can be supplanted, a theory refined, a well-conceived vision, a blueprint for collective action, can possess its own momentum, capable of shaping a future its author would never witness. The structure that Zygmunt Janiszewski built was composed of thought, strategy, and a fierce love for his country, and it has proven to be more lasting than any monument of brass or stone. He is the unseen architect of a towering intellectual edifice, a testament to the power of a single, brilliant mind to organize the world and leave behind a legacy that continues to grow.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.